Alright, here are the solutions to quiz 2 from July 8th. So number 1, we have a pair of charged particles that have equal charges of 5 microcoulombs. And they're separated by a distance of 6 meters. So let's draw that out. And so we want to find the electric potential at the point directly between them. It should be pretty apparent that that point is 3 meters from each of the individual charges. Alright, so the electric potential of a point charge is given by KEQ over R. So we'll use that to figure out the potential of each of these points and work out the potential between them. So one useful thing about the electric potential is that it's a scalar rather than a vector. Which means we don't have to do a lot of trigonometry to work out what the components of the electric potential are. There are no components. It's just a number. So then to find out the electric potential at that point between them, we just need to calculate the potential due to each one. We'll call this V net. We just need to work out the potential due to each of the individual charges at that point. So let's do that. We have, let's see, KE, I'll pull that out. I'm going to go on a separate, another sheet of paper so I have more room. Alright, so that's what I'm working on. Okay. Alright, so let's substitute. We have our electrostatic constant, which we already know is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And then we have our sum of potentials. So Q1 and Q2 are the same in this point, in this problem. So this is a little simpler than other problems. So the electric potential between them is going to be about 30,000 volts. So that's a pretty strong potential. For part B, we want to see how much work we need to do on a third charge to put it at that point, assuming that it comes from very far away. So the work we do moving a charge from point A to point B in an electric field, or in, sorry, let me rephrase that, in a potential, is just going to be the magnitude of the charge we're moving times the potential difference between those 2 points. So in this case, we're moving Q3 in from very far away. So we'll take its initial potential to be the potential at infinity, which we kind of define to be 0. Then the work we do is just going to be Q3 times the potential of that point between the 2 point charges. And then working that out, we get, let's see, Q3 is 10 microcoulombs. And the potential of that point is 30,000 volts. So we have to do 0.3 joules of work on the point charge to move it from very far away to that point right between those two other charges. So what happens if we release it? We have to do work. We have to expend energy to move it to that point. So if we release it, what's going to happen is that the whole system's just going to fly apart because all of these charges are positive. They're all going to repel each other, so the whole system's just going to fly apart. So in another sense, this 3 joules of work we're doing is the amount of energy we need to expend to not only move it there, but also keep it there against the repulsion of the other two charges. All right, number 2. We have a BB gun that fires a pellet of mass 2 grams. And let's convert that to kilograms now, so we don't have to do it later. 0.00200 kilograms at a speed of 45.7 meters per second. And we want to find out that if we fire that pellet, or we shoot that pellet through a potential difference instead of from a BB gun, if we release it inside some potential and it accelerates due to it being charged, what potential difference do we have to accelerate it through if the charge on the pellet is 1 microcoulomb? Alright, so the first thing we need to do is we need to work out how much kinetic energy does the pellet have if it's moving at 45.7 meters per second, because ultimately that's the work we're going to have to do on it. We have to do work on it equal to its change in kinetic energy. So let's work out its kinetic energy at 45.7 meters per second. We already know the kinetic energy is going to be 1/2 mv squared. Let's see, its mass is 0.00200 kilograms. Its velocity is 45.7 meters per second. Let's square that. And so its kinetic energy is going to be 2.08 joules. And that's the amount of work a potential difference has to do on this BB to accelerate it from rest to that speed. So work is equal to Q delta V, the charge times the potential difference. So we know work, 2.08 joules, that just comes out of the work energy theorem. The net work on an object is equal to its change in kinetic energy. We know Q, it's 1 microcoulomb, so we can work out what potential difference the BB would have to be accelerated through in order to reach that speed of 45.7 meters per second. So let's solve this for delta V. It's going to be W, delta V is going to be W over Q. So let's see, W is 2.08 joules over 1 times 10 to the minus 6 coulombs. I'm sorry, this should be 2.09, not 2.08. It's not a big difference. And it turns out that if we want to accelerate it through to a speed of 45.7 meters per second, we need to accelerate the pellet through a potential difference of 2.09 times 10 to the 6th volts, or I'll call that 2.09 megavolts. Alright, number 3. We have a capacitor of capacitance 4.7 millifarads. Or 0.00470 farads. And that's the number we need to use to do calculations. Okay, so we're putting it in connection with a 12-volt battery. And we want to see how much charge is stored in this place. Alright, well, the capacitance is defined to be charge over voltage. But we can solve for Q. So you get Q equals capacitance times voltage. So to find the charge stored in this place, we need to multiply the capacitance of the capacitor by the voltage across it. So we have our 0.00470 farads times our 12 volts. And that gives us a charge on the capacitor's plates of 0.0564 coulombs. The farad is actually a pretty large unit. Common everyday capacitors are usually measured in microfarads, nanofarads, which is 1/1 billionth of a farad, or even picofarads, which is 1/1 trillionth. So for a 4.7 millifarad capacitor is actually a pretty large capacitor in common everyday terms. All right, so B, we connect it in parallel with, we connect our capacitor in parallel with a second capacitor of 10 millifarad capacitance. So let's sketch out our circuit. Here's our battery, positive and negative terminals, and then these are connected in parallel. So there's going to be a branching of the circuit that'll come back together and return to the battery. So 12 volts, so that's not part of the problem. And here's our original capacitor C1, and here's our new capacitor that we've connected in parallel, C2, and that's 10 millifarads, or sorry, 0.0100 farads. And we want to find the equivalent capacitance of this system. So we need to work out what the capacitance is of this parallel branch, and where we have two capacitors connected in parallel. Well, it turns out that the equivalent capacitance of two capacitors in parallel is just the sum of the capacitances. So our equivalent capacitance should just be C1 plus C2, which is going to be 4.70 millifarads plus 10 millifarads, and so we'll get an equivalent capacitance of 14.7 millifarads. You'll note here that I didn't actually convert to farads, I just worked with millifarads. When you're working through and calculating equivalent capacitances, because you're only dealing with capacitance, you're not multiplying by voltage or trying to find charge or something, you don't need to worry as much about converting your units as long as you're consistent all the way through. So whereas I wouldn't get the right answer by adding, say, 4.7 millifarads to 0.01 farads, I do get the right answer as long as my units are consistently millifarads, or if they were consistently farads, I would get the same answer. All right, for part C, if we change out the 25-volt battery, the 12-volt battery for a 25-volt battery, we want to find the charge stored in our original capacitor. So I'll just start on the page. All right, so let's see. V now is 25 volts. And we still have a capacitance of 4.7 millifarads. So again, Q equals C times V. And then we can multiply. So we have our 0.00470 millifarads times our new voltage of 25 volts, which gives us a charge stored of 0.118 coulombs. So that's part C. Alright, number 4. We want to find the equivalent capacitance of a circuit. I'm going to sketch the circuit here, so just bear with me while I do that. 2 microfarad capacitors. We have a 3 microfarad capacitor. And then we have 2 capacitors connected in parallel. One is 7 microfarads, and the other is 5 microfarads. These are all connected to a 12-volt battery, although the voltage doesn't matter that much because we're not calculating charge or current or anything. Alright, so that's our circuit. So in problems like this, it's usually helpful to find the smallest solely parallel or solely series group of capacitors that you can, and kind of work inside out. So in essence, we want to take say this parallel connected group of capacitors and convert it into a single equivalent capacitor. So doing that, let's redraw. We'll call this this thing here will have a capacitance of Ca, we'll say. So then we'll have 3 capacitors in series, and we can move on from there. So what's Ca? Well, we know that when you have capacitors in parallel, the equivalent capacitance is just going to be the sum of the individual capacitances. So this is going to be 5 microfarads plus 7 microfarads. So that should give us 12 microfarads. So then we have a series circuit where we just have 3 capacitors, effectively have 3 capacitors in series. So C1 is 2 microfarads, C2 is 3 microfarads, and we already found Ca, which is 12. So unlike in parallel circuits, series circuits are a little more of a pain because we have to work with it like this. So our equivalent capacitance for this circuit is going to go like this. 1 over the equivalent capacitance is going to be 1 over C1 plus 1 over C2 plus 1 over C3. So then our equivalent capacitance, we're going to have to do this sum, find a sum, and then invert the whole thing to find the actual equivalent capacitance. So let's work through this for now. We have 1 over 2 microfarads plus 1 over 3 microfarads plus 1 over 12 microfarads. And so 1 over 2 plus 1 over 3 plus 1 over 12 is going to result in this number. You'll notice I put a -1 on here to indicate that the actual unit of this is inverse microfarads. Not farads, but inverse, because all of these are on the bottom. So I could also more correctly write this as 0.917 over microfarads. So we need to invert this to get the actual equivalent capacitance. I'm going to start a new page. So then CEQ, the equivalent capacitance, is going to be 1 over this 0.917 inverse microfarads. And that's going to give us an equivalent capacitance of this entire circuit of 1.09 microfarads. So that's a general rule for circuits. You work from small bits of the circuit outwards, and if it helps, every time you redo it, you redraw the circuit. All right, so that's it for quiz number 2.